Lloyd Lacomb is from the University of Arizona and TIPD. Yes, and this paper is also has a couple of co-authors, as you can see here, from Michael Bove at MIT and Daniel Smalley at BYU. So he's done a lot of work in display technology, so take it away.
Thank you. So I'll be working on the display side. So as you're looking at it on the sort of the right side of Chris's original chart there, I won't sort of talk about how the data is acquired in our system, but really about the display side. I'll get next. So I'll talk about two different systems that we've developed in collaboration with the University of Arizona and with Michael Bove at MIT and some of his students. The first system is a photorefractive display. So photorefractives are materials that change light intensity into refractive index contrast. To do that. So here on the far end is an interference pattern that's generated, and you can see the light and dark regions there. The materials, that light then separates electrons and holes, just as an easy way to think about it, and they move from the light regions to the dark regions. That sets up a local electric field, and if there's a molecule with a dipole moment, then it rotates in the presence of that local electric field, and in particular molecules, that then transfers that rotation into a refractive index change. And so now I've taken my intensity change into a refractive index change, so I now, when I re-illuminate that, I can regenerate my hologram. So photorefractive materials were first discovered in the 60s. They were crystals, very small, very expensive to use. In the 90s, they developed polymers then that are composed of 4 or 5 different materials. They can be scaled to much larger size. Here we've scaled one to about a foot on a side that we've used for some of our displays. So to make a photorefractive hologram, we're going to have several parts. The first part is really recreating a camera array. So we have a model in the computer, and now we need to create all the images that I'm going to project to you using that hologram. And so that's what's shown on the far side. We then actually make an interference pattern between a reference beam and the object beam, and that object beam is modulated by a spatial light modulator that relays that information. So I make then an interference pattern. In this case, I'm showing it making a line. I write the whole array, and then I move it and I illuminate that with a copy of the reference beam and regenerate the entire holographic image. Photorefractive materials are nice. You can write in one wavelength and, of course, shift them to another wavelength. I can use polarization to generate 2 colors, and there's a property of the material as those electron and hole pairs are moving. If I set those up to move orthogonally, I can actually write 3 colors in the same film with one source at the same time. So they have a number of very nice properties for generating holograms. Here, this is a CAD model of Castilla Segovia. Here's 3-color. We are working with Nito Dinko for the chemical properties, and MRI images of a skull. It was Halloween, so I wanted to do something to scare everybody a little bit and see. To be able to do that. So we've been able to import a number of those. You illuminate that then with an LED source. We didn't really want to be shining lasers back out at the audience. You can, on the CIE space, you can pick your points. You can get pretty good coverage. And so here's an example of the system. This is shot in room light. I just stopped the system down. So you have about a 300 candela monitor, and you can see we can make the images very bright in room light. And these have about a 30-degree angle, so you can watch at about 30 degrees for the systems. We were able to achieve brightnesses up to 2,000 candelas per meter square, so we're able to get it pretty bright. That's mostly the diffraction efficiency of the film and the illumination of the source are the 2 major factors that control that. We tried to do streaming telepresence. We're not video people, so ours was unimpressive compared to what people are doing. We took the brute force approach, so I just took 16 cameras, put them around 30 degrees, and then took images of things to be able to do that. For those of you that know Daryl Hopper, this is 16 images of Daryl Hopper collected from the system. They're collected, these cameras are just 640 by 480, so 16 versions of Daryl, then around that 30 degrees. We were able then to basically recreate this sort of camera array. So it uses an algorithm that's called slice and dice, and it's just easy to think about it as moving a camera array around. So here I have those 16 camera positions. So I slice those up in the way the system wants it, send them out over the internet. So here I just open a TCP socket to the display engine, pipe it out over the internet, let the internet take care of all the organization and everything else. I'm only sending about 2.5 times HD data, so I could do that actually at reasonable speeds up to the printing engine. And Daryl didn't want us to take images of his hologram for some reason, so this is one of my collaborators, Pierre. And so you can see some of the shortfalls of having just 16 images. You're getting, it's always hard to take a photograph of a hologram, but you're seeing a lot of the subsampling that since we only had 16 cameras in that system. So that system was up and working. We're worked on a few other ideas, looking at adding some Connect cameras, trying to make models of people, hoping to reduce the bandwidth that was needed to send that over the internet. You really need low-frequency models. So we had people that really had skin that was very uniform in complexion. Anything higher frequency than that, or anything with people with hair, our software just wasn't good enough. You had to have really low-frequency models, as I said, to get decent models that you could send over and recreate on the other side. So, about 3 years ago, we started working on a new system. Daryl came up with a name, this holographic video display and a guided wave system. And so I'll talk a little bit more about that. This is the use case that they really brought to us. So I have 3D terrain and overlay data for pretty much every part in the world. I now have some other device that's streaming in 2D data or 3D data, some device we can't talk about potentially, but it's bringing in data. We need to align those systems and then display them to an analyst. And then they want to be able to move that three-dimensional image in 6 dimensions. And we said, okay, might be doable. And he says they have to be able to do it for 4 hours without getting sick. I said, okay, that could be a little tricky, but tell us what the requirements are. So we kind of walked through that. So his requirements were full parallax. They'd done a lot of work at AFRL showing that full parallax was needed for both long observation and to provide a lot of the different visual clues that were needed to make decisions. A total of 1 million pixels to 2 million pixels, depending on the configuration. Conical viewing angles, this is the whole angle, 30 degrees, and they really wanted 60 degrees of view, 10:1 contrast in room light, and video frequency updates. And then they just threw in all the other things. So you had to be about 50 centimeters away, about half a meter away. You had to have no limit to the number of viewers. So you could have the analyst could be looking at it, his boss and his boss's boss could all walk up behind him and see things from their particular perspective as well. And no lag. And he also said he wanted it to be the size of an LCD system as well. So just to throw all the things in there to be able to do that. So we looked at approaches, and we partnered with MIT on their anisotropic leaky mode waveguide system, and I'll spend a little bit more time. They've developed a horizontal parallax only system here that works in 3 colors. And they've demonstrated video rate, horizontal parallax only system, capable of potentially 50 gigapixel per second. And that was attractive to us given some of the data rates that we'll have in the next couple slides. We then needed to figure out a way to add full parallax to that system, and we've come up with an interesting way with an electro-optic modulator that really works sort of like Venetian blinds. It will then operate that other operation to scan it in the vertical direction. So a quick overview, the AO modulator, see, don't have a pointer here. So the AO modulator will couple light in, it's not going to work, is it? So we'll couple light in using a prism or a holographic grating, ultimately from the back side. That light travels down, the surface acoustic wave is generated by the acousto-optic modulator. So now I've generated that diffraction pattern that's going to diffract the light out, and I have control over that at the gigahertz levels to be able to do that. I can set up the diffraction pattern in such a way that I can have multiple emitters between the in coupling and the surface acoustic wave device. So each one of those can do multiple elements. I can then put multiple lines on one of those, and I'll show a picture later. So now I have lines and sort of the equivalent of pixels in a two-dimensional display. And I can use that then to make my light emitter. I can then couple multiple of those together and ultimately, hopefully, make a very large display for the program. So data generation is an issue for us, and I'll talk about that. But we basically need X, Y, theta, and phi at 1 million or 2 million points. And so generating that data has turned out to be hard, and maybe I'll try to talk to the Litro guys. Sending that data from one spot to another has also turned out to be incredibly problematic. We're optics guys, so we don't really, do much of the other stuff. The oversimplified rendering engine, we've pushed everything onto GPUs. Basically buy the best CPU I could, stick as much memory as I could on there, and as many high-end graphics cards as we can do to really run that virtual camera algorithm. And so we break up the scene into different parts, divide that up across the multiple processing units in the GPU to parallelize things as much as possible. We continue to do a lot of work there. For us, the recent GPU cards have more RAM on them, so we're able to download the scene for that particular part that GPU is responsible for onto the GPU, so we don't have to go back and forth over the PCIe bus unless there's an update to the data. And so that's one of the things that's allowed us to have improved performance. So I call this space bandwidth product. I guess some people in the industry use that as different amounts. This is really just data transmission. The space bandwidth product is usually expressed in cycles, so there's a Nyquist factor of 2 in there between what I'll say and what's in the space bandwidth products. But for this particular project, the Air Force specified the number of light-emitting elements. I'll just call them pixels in this discussion, and they also specified the angular range that we had to cover and gave us the distance. So if you kind of look back what you have to have for incredibly smooth motion, and if you want a view about every pupil, so as you move around, you get some pretty ugly numbers. If I want a 1 megapixel display, say nominally 1280 by 768, I need 100 horizontal views, 100 vertical views at 30 hertz, so I need 300 gigapixel equivalents. So 900 gigabytes a second, or 7 terabits if I don't have any overhead for any of my bytes to be able to do that. If you look at the system they want, you get about a factor of 16 more, twice as many light-emitting elements, twice as large of angles, twice the refresh rate. Everything goes up by 16. It's still mostly in the linear regime at that point. 115, you talk to the transmission guys, they all do bits. So everybody you talk to has a different increment of unit. So 115 gigabits per second. So that sounded bad. Terabits per second. So that sounded bad. So I said, oh, it really can't be that bad, right? So I was like, oh, it can't be that bad, right? So, okay, so what is HD TV? I need about 3 gigabits a second, right? So, okay, that's about 3 gigabytes bits. Okay, so 3D TV, I'm just going to say we're transmitting 2 of the same thing. I'm not going to get in discussion whether I'm time sequencing or space sequencing. But to do that, okay, 6 gigabits, not so bad. If I want horizontal parallax TV, then I need 200 views. Okay, so now I'm up to 600 gigabits a second. And if I have a computer in there, getting information out of the computer, I'm sort of limited by DisplayPort sort of speed. So 25 gigabits, maybe 50 it looks like we might get. So now I've got a whole bunch of cables going between my system. And now if I want to add 200 times that in the other dimension, so yeah, turns out about 115 terabits. So I need 40,000, I need 40,000 HD TV signals to drive a display like that. If you look at what they use in fiber optics for data centers, right now commercially they do about 100 gigabits a second. They're sort of piloting 400 gigabits a second. People in the labs are working on a terabit a second. So I need 100, cutting generation fiber optic cables. Okay, so, being a university professor, all right, somebody solved this problem, right? So look in the back of the book, find out the answer, and then go from there. So maybe it's been solved. There's the square kilometer array, so they're stringing together 200 to 2,000 radio telescopes. Each of those is generating data out at about 160 gigabits a second. That's designed to run pretty continuously. So they're scaling that up. So they're thinking by the 2020s, they might be able to generate a petabit a second. So, okay, so somebody's working on this problem. I contacted them. They don't know how they're dealing with the data yet at that level. Their diagram says it comes into a supercomputer. So that's kind of how they're handling that. This big box on the diagram. There's this supercomputer that handles all of that. So I looked at, well, what else deals with 150 terabits a second? Google and Facebook just announced they're collaborating on a new fiber that connects California and Hong Kong. So they're dropping this giant C cable. And so that'll do 120 terabits per second. So I said, okay, well, somebody solved that problem. That's nice. Unfortunately, that's what it looks like. It looks like a giant anaconda that runs under the Pacific Ocean. So that's the kind of bandwidth that we're talking about. So an undersea cable is the kind of information we need to get to the end of the equation to be able to do that. So where are we right now? We've generated one device. That's an example there that does 374 full parallax display elements, and we can feed that system. We're looking at integrating multiple devices together to see if we can start putting a display together and how well they all fit together. And a lot of the work right now is simplifying the manufacturing process to something that could eventually be commercializable. Right now it works at sort of a university research lab where, if your yield is 1 out of 10, your student can graduate, and that's a good deal. Probably not ready for commercialization at that kind of level to do that. So I'd really like to thank all the people that have worked with the University of Arizona, the MIT team at the Media Lab. Daniel Smalley is one of Michael's students who's taken up a professorship at BYU and doing a lot of work on the AO and EO material, and then my colleagues at TIPD, and we've been fortunate enough to have been supported by the AFRL, by DARPA, and by IARPA. Thank you.
We have some questions.
Yes, sir.
Thank you for sharing. Would you mind using the microphone?
I know you have a big voice.
Thank you for sharing. I do 3D.
Yes.
And so, people were always talking holograms,
Right.
and hologram replacing 3D, but the problem is holograms were always designed for us to go around the hologram subject, whereas the audience in immersive wants the subject to go around us.
Yes.
So where does this fit into that kind of evolution? Are we able to start doing holographic displays that will envelop the audience and make us part of the picture?
We're not working on that problem. That would be an even harder problem than probably the problem that we were tasked with. So we're really looking at sort of a combination of being able to move within a limited range of sort of an LCD monitor size range, and then to have control over the data in video rate applications. So not fully immersive yet, unfortunately.
I just have a concern about the amount of data that you're saying we've got to be pushing. And if we are going the capture method that you're talking about, can't we also think more variable, like only capture the stuff that is moving in the deep background, just consider it more 2D?
Yes, ma'am. There are ways to do that. The way our hardware system is set up is probably closer to the way the old phosphor tubes work, that we basically have to refresh everything in your eyes, the integrator. So while you may only have to transmit changes, and we basically have a signal in there that doesn't retransmit the data, we have to continually display that much information, just the way the system works. So we could sort of, get some giant fat cable and sort of connect to the Litro part, because they've already segmented the data really the way we want it in a lot of ways. So we would skip a lot of the calculations that we have to do. And can see. So that, that might be another possibility to do that.
So how are you going to solve the data management problem for your deliverable?
Well, so luckily, we only have a Phase 2 program, so our deliverable is a little smaller, and we can keep up with the size that we committed to for the Phase 2 program. But yeah, I'd like to brainstorm with people here of just what, luckily it could be short distance, so I don't have to go from here to Hong Kong.
Yeah.
But, what do people use out there? Lytro's clearly, a third of they're doing 900 gigabytes, so I'd need 900 gigapixels. Yeah, 300, okay, so yeah, so I need 900 gigabytes, but that's close, that's closer than, yeah. Yeah, well, yeah, it's just turn up the knob, right? There's a knob, potentiometer somewhere. We'll fix that one. Yes, sir.
Yeah, besides turning the number up to 11.
Yeah.
What is the capabilities within your system? Are you able to use some dedicated things to, say, create the background as a permanent fixture while we have the variables of characters going in and out of it as the option instead of having to do the whole picture itself?
So right now, no. So our system wasn't. So we weren't. That wasn't the way we thought about it as a system.
It would almost be like having to have two separate systems where you're seeing one display over
Right.
another, which I suppose could be done in a simple system
If I
by
were-
having two
yeah.
separate planes of glass. Or
If we were
something like that.
clever, there might be a way if the background was static, yeah, or moving less quickly. There, you could have maybe two
It's
systems.
stitched once in and
Yeah.
circular, or even on the virtual reality things where we think we're looking around differently, but what we're doing is following somebody. Whenever
Right,
we move,
who's
they're
already
always
moved.
moving that direction, and they're really just standing still. and
Yes.
The background kind of moves behind it.
Okay,
Thank you.
thank you very much.